Welcome everybody. So far for colligative properties, we've talked quite a bit about um, what a colligative property is and what you need to know for the regions, and also how to do some of the math here. In class, we also discussed specifically problems for boiling point elevation and freezing point depression, ones that were easy, ones that were difficult. What we didn't really get into was vapor pressure lowering, although I did a problem in the last video where I showed you how to find the vapor pressure of a solution given a certain amount of solute and solvent. So for example, I had a solution where I had 36 grams of water, and then I added to that a certain amount of solute, zero point 0.1 mole of solute. And I could make this more difficult, and you're going to see a problem for this video that's going to be a more difficult version of this particular example here. And what makes it more difficult is that both of the solute and the solvent are volatile. And let me go right to that, and we'll come back to osmosis in a minute here. But let me show you what this looks like. This is sort of a more difficult question from the last one. And what makes it more difficult is that in the previous problems for vapor pressure, if you noticed, the vapor pressure of the solution was equal to the mole fraction of the solvent times the vapor pressure of the solvent. And what this was assuming was that the solvent was the part that was volatile. We didn't worry about the solute being volatile. And what volatile means is that it evaporates. We also use volatile as a vocabulary word to mean not stable, but in this case it means easily able to evaporate. And that could relate to stability of the intermolecular forces. But here what we have is a situation where the vapor pressure of the solution that we have is equal to two parts. The first part is the solute that is volatile, and I'm going to highlight that in red. And then we have the component of the solution, which is the solvent that is volatile. And so we actually have two volatile parts. What this basically means is that both the solute and the solvent are evaporating. So what does a problem like this look like? Well, we have an example right down here that I'm highlighting in orange. And let's go through how to do this problem. They ask you what the vapor pressure of a solution is, and they tell you that it contains 3 moles of toluene. Notice they give you a vapor pressure here. That's very important because what that's telling me is that it is actually going to evaporate. And then they also give me the other component. So we have the 3 moles of toluene, and then they give me the other component, which is the 7 moles of benzene, and they also give me a vapor pressure. Since they gave me vapor pressures of both of them, it means both of them have the potential to evaporate. So we need to use both of them in our calculation. Well, let's figure out what the vapor pressure of the solution is. Well, if I look at this, the vapor pressure of the solution is going to be equal to the solute, and that solute's the thing with less moles. So in this case, it's going to be the toluene. So the mole fraction of toluene is 3 moles over the total of 3 and 7, so 10 moles, times the vapor pressure of toluene, which is 150, plus the mole fraction of the benzene, which is the 7 moles of benzene over the 10 moles total, times its vapor pressure, which is 200. And so now we have both of our mole fractions here, and now we can plug into our calculator or try and do the math on our own actually. We would have 450, 3 times 150 is 450 divided by 10, and then 7 times 200 is 1400 divided by 10. This becomes 45, and this becomes 140, and together they would add up to 185 kilopascals. Notice that the vapor pressure of the solution when both of the solute and the solvent are volatile is somewhere between the higher vapor pressure from the more volatile benzene at 200 kPa and the less volatile toluene at 150 kPa. Now I can make this question more difficult And I could do that by not giving you moles of each one. I could give you grams of each one and make you find the moles. That would make it more challenging. I could also make you find the mole fraction of each one. And we could do a problem like that in class. That's more challenging. But in the end, you're going to go down one of these paths here. You're going to either use the more complicated equation, where they're both volatile, or the easier equation where only one of them is volatile. We'll practice all types of variations on this, just like we did with the other type of problems. You'll see what that looks like. Okay, let me talk to you about one last colligative property, and that is osmotic pressure. So to talk about osmotic pressure, we need to talk about osmosis first and define that. And osmosis is the movement or the diffusion of water, the solvent, from a region where you have low solute concentration to a region where you have high solute concentration. So for example, if I had a 0.1 molar solution in a container like this with a porous barrier, and over here I had a 1.0 molar solution over here, the water inside this component here, or container here, and there'd be water over here, the water would move from high to low. Or from low to high water, I should say. So the water would move from the 0.1 over here to the 1 molar. The idea would be to dilute out the solution until the concentrations were equal. So the 0.1 molar, as it lost water, the concentration would go up. The 1 molar, as it gained water, the concentration would go down. So here is my equation for the osmotic pressure, and this symbol right here is pi, didn't come out so well. M is molarity. R is the universal gas constant, 0.0821, and T is the temperature in Kelvin. And again, for this problem, they could range from something very easy, like find the osmotic pressure, to something that's more complicated, like find the gram formula mass of the solution. So we could go in a lot of different directions with this one, and I'm actually going to put up a sample problem for you to do, and hand in to me for for Monday, or when we come back to class. So that's what we're going to do there. It'll be part of this video. So those are all the different colligative properties. Look, you should know the equations. You should know the 4 colligative property equations, and there's a bunch of equations to know for the different types of concentrations: molarity, molality, mole fraction, parts per million, percent composition, parts per billion. This graph right here is sort of a blast from the past, and this is showing you, in the beginning of the year, we had done one of these graphs where we did the phase diagrams. And these lines that I just highlighted are the transition between solid and liquid and gas. And what the graph also is adding this time is what would happen if we had a solution. And what you'll notice is that if I highlight that in purple, the solution has lower vapor pressure, because this is the vapor pressure curve. It also has a higher boiling point. It has a lower freezing point, lower triple point, and there's a change in temperature between the delta T that they show here and the delta TB over here, boiling point and freezing point. So this is just kind of showing you how, originally we had this region right here was our liquid region, and that's what we're really dealing with in this whole entire chapter, is liquid. And now that's been expanded to where the purple line is. So the liquid stays liquid for longer. Now, one last slide I want to show you is just a demonstration of osmosis. And this is what I was trying to show you before, that, here is my dilute solution versus my concentrated solution. Over time, water will move into the concentrated solution, and you'll see there will be this change here. What osmotic pressure is it's the pressure that you need to apply, in this case to the left side where the level of water is higher, to basically return it back to before where osmosis took place. kind of preventing and stopping osmosis from happening. The pressure that you need to apply is called the osmotic pressure. This little segment down here, if you want to read this, it goes into some detail about each of the steps there and how the osmosis is stopped. So you have a bunch of practice problems that are attached to this. We've done a bunch of them, but there are some left over. I'm going to post a couple to go along with this video just so that I know that you watched it and that you understand the different types of colligative properties. All right, thanks so much for watching.